Last class we looked at the process of lithography. So lithography is a process where we transfer a pattern from a mask onto your wafers. So the pattern is generated by the IC circuit you are trying to design, and for a given circuit there could be multiple patterns or multiple masks. We saw that in lithography it is essentially a two-step process. In the first step, the pattern is transferred onto a photoresist layer that is applied on top of your wafer. So this is a temporary process. Photoresist is a photosensitive material that can either dissolve when exposed to light, making it more soluble, that is called your positive photoresist, or you can also have a negative photoresist where the photoresist becomes less soluble when exposed to light. The first step of course is transferring the pattern onto the photoresist, then the pattern has to be transferred onto the wafer. So this usually involves removing some material from the wafer, a process called etching, or adding new material to the wafer, again at specific locations determined by the pattern, and this process is called growth. Last class we looked at lithography, which is the first step, and today we are going to look at the etching and the deposition or growth process. We will first look at etching and then move on to growth. So etching can be defined as the removal of the material from top of the wafer. Another way of writing it is that it is removal of the top layers from the wafer. Again, as I mentioned earlier, etching is usually combined with lithography, so that lithography is used to expose certain portions of the wafer which are then removed. Similarly, you can also use lithography to expose certain portions of the wafer where you add material, and that will be the deposition or the growth process. So there are essentially two main types of etching. Etching can be a wet process, it's called wet etching. The other process is called dry etching. So we will first look at wet etching. In the case of wet etching, as the name implies, usually some sort of wet chemicals are used to remove the material from the wafer. So the wafers are usually immersed in a tank of etchant. And this is usually done under certain conditions. So specific concentration of the etchant, specific time. Sometimes this can be done at room temperature, but most often etching is also carried out at elevated temperature to speed up the process. So to give an example, consider you need to etch silicon. A number of different etchants are used, but the most common one is potassium hydroxide. So for etching silicon, usually 30% KOH is used at a temperature of 90 degrees. So the chemical is taken in a bath which is heated to 90 degrees, and then the wafers are immersed and are used in order to remove the silicon. Under these conditions, the etch rate is approximately 100 micrometers per hour. So if you think about a silicon wafer, a typical thickness of a silicon wafer is around 500 micrometers or approximately 0.5 millimeters. So a silicon wafer that is 500 micrometers thick, you can etch through the entire wafer in approximately 5 hours. So usually after wet etch, the wafers are removed from the etchant, then they are cleaned again with distilled water in order to remove any of the excess etchant material. So usually some sort of chemical. Then the wafers are dried and then used for further processing. So wet etch is used for removal of material from large areas of your sample. Again, we can give a typical number, say a few micrometers. So let me say 3 micrometers. For smaller precise etching, so for etching from smaller pattern regions, usually dry etch is preferred. So whenever we think about etching, etching uniformity is really important, and these again depend upon the process conditions. Etching uniformity matters, and this depends upon the process conditions. The typical process conditions are the etchant temperature, the concentration, you can also have some sort of external agitation. This could be a simple magnetic stirrer that is used to stir the liquid so that there is greater fluid flow. So some sort of stirring, and all of these affect the etch rate. So it is usually very important to keep all of these numbers constant so that you have a constant etch rate. For example, if your material is being consumed during etching, then the concentration will change, and a change in concentration can again lead to a decrease or an increase in etch rate. Similarly, if for some reason the etchant temperature is not constant but keeps fluctuating, that will again affect the etch rate. So usually some sort of initial experiments are done for different values of these numbers in order to fix a etch rate for the material before the actual wafers are used. And again, these depend a lot upon the process conditions. So let us look at some of the various issues that are present in etching. So this is true for both wet etch and dry etch. It is less so for dry etch than wet etch, but we can use this to illustrate some of the important process issues associated with etching. The first, of course, is that you have an incomplete etch. To give you an example, consider a wafer with some layer on top. So we want to remove a certain portion of this layer in order to expose the underlying wafer. So we can do some sort of patterning. Let us say we do lithography using your standard photoresist. So I would say litho here, and we do this in such a way that we open a window onto this layer. So we use a resist so that we open a layer, we open a window onto this layer. We saw this, how we do this in last class. So we take either a positive or a negative photoresist, we use the corresponding mask, we spin on the photoresist layer, expose through the mask, develop, and then remove the resist so that we get the window. We can now etch through this layer in order to expose the wafer. But if your etching time is not sufficient, so you have an incomplete etch, instead of removing the material completely, you will be left with some of the layer still intact. This is the resist, this is the layer. So this is an example of an incomplete etch where the etching has not gone all the way to the wafer, but it has stopped somewhere here. Now an incomplete etch could be because time is not sufficient. Most often that is the case. For example, if you estimate an etch rate of say 100 micrometers an hour, but your actual etch rate is lower, say around 60 or 70 micrometers an hour, the time you have given would not be sufficient for the layer to be removed completely. There could be other reasons as well. For example, your concentration might not be correct, concentration varies. Temperature is not constant. So all of these, which are essentially your process parameters, can affect your etching process, giving you an incomplete etch. So when you essentially have an IC fabrication process, some sort of experiments must be done before you actually use your given material to determine the etch rate. So one process issue with etching is the fact that you can have incomplete etch. Another one is where you go the other way and have something called an over etch with undercutting. So your first process issue is an incomplete etch. The other one could be an over etch, usually accompanied with something called an undercut. So to give you an example, again let us go back to the wafer. So this is your wafer. This is the layer where you want to create a window, and again you have some sort of resist that you use to open the window. So this is your layer, this is the resist. So let me just shade the resist so you can differentiate it from the layer. An ideal etchant, if you think about it, should essentially give you these really straight side walls. In order to do this, your etching must be anisotropic. When we say anisotropic, we mean that etching should take place only in the vertical direction and there should be no lateral spread. Usually that is not true. In the case of wet etchant, you have etching that is essentially isotropic, though you may have different rates going in different directions. So instead of a pure anisotropic etch, you might have an isotropic etch. So instead of having a straight side wall, you might end up with a side wall with a certain amount of taper. So this is your layer. So this is the wafer, this is the layer, again that is the resistor. So that instead of having a side wall that goes straight, you have material removal in the lateral direction as well, giving you a sort of a taper. So this is the case when you have isotropic etching, and again etch rates would be different for different directions. For example, we looked at KOH, which is used for etching silicon. You could find that KOH will not only etch the 100 surface. So let us say you have a silicon wafer that is 100, then the 100 direction is perpendicular to the plane of the wafer. So KOH will not only etch 100, but will also etch the 111 direction. So KOH is an example of an isotropic etchant. So the etch rates are different, but it will still etch the other directions as well. So the etch rate for the 100 direction is greater than the etch rate for 111. And in fact, there is a specific angular dependence which will develop in the case of a wafer when you are trying to etch the 100, because it is also etching along the other directions. So when we have an isotropic etch, so we saw that we do not have straight side walls, but we also have some etching along the lateral directions, giving you a side wall that is sloped. Now if you go for etching longer than the time that is required, you will have more material being removed from the sides, leading to something called an undercut. So we want a pattern that is being defined by your photoresist, but because you are also removing material from the sides, you actually end up having a wider pattern. So this is a case of an isotropic etch. If you go for an over etch of this, again to give you an example, let us say you have determined an etching rate of 100 micrometers an hour. So you plan for a 5-hour etch, but your actual etch rate because of your process conditions is faster. Let us say it is around 120 or 130, then in the same 5 hours you are going to remove more material, not only in the vertical direction but also in the horizontal direction. So an over etch here can lead to a wafer So again this is the wafer, this is the layer, that is the resist. So comparing these two, we have more material being removed from the sides, and ultimately if you over etch a lot, you can even have the resist layer completely lifting off because there is insufficient material below it. So one problem is an incomplete etch where you etch for a shorter time. On the other hand, for an isotropic etching, you can end up having an over etch. Now another problem when we look at wet etch is the selectivity of the etchant material that you use. A third issue is the selectivity. You have to choose the etchant material correctly so that it is selective to the layer you want to remove. So this is very important because you need to be able to protect the material that is below it, and you also want to be able to provide a stop for the etching process to happen. So usually that is not the case. So sometimes you have etchants that are not completely selective, but if they have a vast difference in etching rates between two different materials, that should also be fine. To give you an example, let us go back to KOH. We saw that KOH can be used to remove silicon, and the etching rate is approximately 100 micrometers an hour at 90 degrees. So it is used for silicon etching. But the same KOH, instead of having silicon, if I have silicon dioxide, SiO2, the etching rate is usually 1 micrometers an hour, again at the same 90 degrees. So you can see that KOH is more selective to silicon than silicon dioxide, though the rates are just 100 times off. Instead of silicon dioxide, if I have silicon nitride, Si3N4, the etching rate actually way lower, it is 1 nanometer an hour. So we can say that KOH is highly selective to silicon etching, less selective to SiO2, and really stops etching when we have silicon nitride. So when we look at silicon etching, usually silicon nitride is used as a mask layer for silicon. It can either be used as a mask or an etch stop for silicon. Similarly, for other layers, you have specific etchants that are used which are selective to that particular layer and will not affect the other layers. So let us look at some examples of some etchant materials that are used for the various silicon layers. So some examples of etchant materials. So for silicon etching, we have already seen KOH as one material. You can also use a mixture of nitric acid plus hydrofluoric acid. For SiO2 etching, typically hydrofluoric acid plus ammonium fluoride is used, NH4F. So this gives you an SiO2 etching rate approximately 100 microns an hour. But it is very selective to SiO2, it does not etch silicon. For silicon nitride is usually impervious to a lot of etchant materials. It forms a very good passivating layer. So hot phosphoric acid is used, so H3PO4 at 180 degrees is used to etch silicon nitride. Usually for MEMS device fabrication, there are some devices where a silicon bridge or a silicon membrane needs to be formed by being supported by a silicon frame. In those cases, the entire wafer has to be etched in order to create the silicon membrane. For such applications, silicon nitride is used as a sort of an etch stop layer, so that once the KOH eats through the entire silicon, it sees the layer of silicon nitride and then stops etching. So silicon nitride is used as a very good passivating layer, not only for silicon but also for silicon dioxide. So far we have looked at wet etch, so let us now look at dry etching. So if we look at wet etch, one of the limitations that we said is that it can only be used for etching large areas, so a few micrometers long. Now this is really not possible when we have to pattern smaller and smaller features. So we need to etch from really small areas. Wet etch also uses a lot of harmful chemicals, so it is environmentally not very sound. So for this, one of the new techniques that has come up is to use a process of dry etching in order to remove materials. So in dry etch, gases are the primary etching medium. There are essentially three kinds of dry etch. One is called your plasma etch. Another process is called ion beam milling. This is more of a physical material removal process than a chemical etching process, that is ion beam milling, and a combination of those two, which is called reactive ion etching. So if you look at the plasma etch, the chemical etchant is introduced in the gas phase and electrodes are used in order to generate a plasma. So this plasma then attacks the wafer surface and then removes the material. So again you have the etchant in gas phase. For example, to remove SiO2, some sort of a fluoride gas has to be used. So usually CF4 is used. Let me just draw a brief schematic of the plasma etch. So you have a chamber The chamber is usually evacuated so that there are no atmospheric contaminants. The wafer is taken on some substrate holder. Usually multiple wafers can be etched at the same time. So these are your wafers. An electrode is brought close to the surface of the wafers. It's connected to a radio frequency source. So this is your RF electrode. The etchant gas is then introduced into the chamber. Some sort of carrier gas is also used. So this reacts with the electrode and basically there is a plasma that is generated. This then attacks the wafers and then reacts with the silicon dioxide and removes the material. You can protect the surface of the wafers usually by using a photoresist, so that once again you can have a window, and wherever the layer is exposed it is removed, and wherever it is protected by the photoresist the material is still there. So in the case of dry etching, the etch rates are usually much slower. So your etch rates are typically 1 to a 10 micrometers per hour. So the etching is usually carried out with a sample at room temperature, unlike the case of wet etching where the chemicals are usually at a higher temperature. So the etch rates are slower. So if you want to etch a really thick film, then wet etching would be the way to go, because dry etching can take a long time, but it is highly selective process and can also be used for really small areas. The other kind of dry etching is the ion beam etching. So the ion beam etching, the chamber arrangement is similar, but instead of a chemical reaction you have physical removal of material by bombarding it with high energy ions. So you physically remove material using high energy ions. So in a way this is similar to the ion beam milling process that takes place in a TEM. So this has no selectivity because it is only a physical process, but the advantage is it is highly directional. So if you want to define really vertical sidewalls, it is highly directional. You can also change the direction of the beam so that it is not impinging the surface vertically, but it is impinging the surface at some angle, and so you could get different etching profiles using ion beam milling. Reactive ion etching is the third kind of etching. So this combines both the processes, both plasma and ion beam etching. So you not only have physical removal of material, but you also choose your etchant gas in such a way that there is some chemical reaction. So it is a mixture of both plasma and ion beam etching. So dry etching is also used to remove the photoresist after the etching or the growth process. So again we saw in last class when we did lithography, we spun a layer of photoresist on the surface. open some windows where you can do some work or some chemistry on the wafer, and after the process is removed, we completely remove the photoresist from the entire material. So usually dry etching with oxygen is used in order to remove photoresist. So usually plasma, oxygen, this process is usually called resist stripping. Similarly, if there is some mistake when the pattern is transferred to the photoresist, for example, if there is an alignment issue and then the pattern is not transferred to the photoresist completely, you can strip the photoresist again using a plasma oxygen clean and then reapply the photoresist and then do the entire masking and design transfer process. So dry etch again is used for that. So we have looked at some of the etching processes. So in the case of etching, we are removing material. Now we are going to look at some of the growth processes. So if etching is removal of material, deposition is addition of material. So you have material that is added to the wafer surface. We have seen grown layers before. For example, we have seen oxide layers or nitride layers before. In those cases, we are consuming the silicon in the wafer in order to form the silicon dioxide or the silicon nitride. In the case of deposited layers, we are not consuming any of the underlying silicon. So unlike the grown layers, silicon is not consumed. So some of the areas where deposited layers are used, usually you have epitaxial silicon or episilicon that is grown. So here you are growing a new layer of silicon on top of your silicon wafer. Dielectric materials are another example of deposited layers. So usually they are made of some sort of metals, could be intermetallics or high K dielectrics. Trench capacitors, again a trench is formed in the silicon and a dielectric material is used to fill the trench. Intermetal conducting plugs, this is used for making electrical contacts. The metal layers themselves, surface passivation layers, all of these are different examples of deposited layers. So there are two main techniques for growing deposited layers. One is your physical vapor deposition technique or PVD. And the other one is the chemical vapor deposition, so CVD. So physical vapor deposition is usually used in order to grow metallic layers. We will see more about it next class. So CVD is usually used for growing layers like silicon or epitaxial silicon, dielectrics like silicon dioxide or silicon nitride, some sort of silicides, gallium arsenide and so on. So when we look at deposited layers, some of the important film parameters that we should keep in mind. One of course is your thickness, how thick these layers are. Along with thickness, an important parameter is uniformity. So we want uniform thickness throughout the entire wafer, and this becomes more important because you are now migrating to larger and larger wafers. Your current IC fabrication involves 300 millimeter wafers or 12-inch wafers, and now you are moving to 450 millimeters or 18-inch. If you are trying to grow a layer, you not only want the desired thickness, but you also want the thickness to be same over the entire 18 inches. Surface roughness or the roughness of these layers, usually some sort of polishing can also be used. Composition, stress. Stress is important because this can lead to delamination later on and you will use the film integrity. Purity and film integrity. So these are some of the important film parameters. It's important to note that your substrate need not be flat. So your substrate could have other features that are on there, so that you are not essentially growing on a flat substrate. So this becomes especially important for surfaces that have, say, a deep trench or a deep well, and you need to grow within that well. In such cases, the thickness and also the aspect ratio of these layers become important. So in the case of CVD, which is chemical vapor deposition, your materials are introduced in the gas phase and these then react to form the film that you want, which then gets deposited. So the materials are in the gas phase, so they form a vapor, which is why it is called vapor deposition, and these then react in the chemical reaction to give you the final film. So some reactions that are typically possible, for example, you can have pyrolysis, so which is a simple silicon hydride giving you silicon plus 2H2. So this silicon layer will then be deposited onto your film. You can have a simple reduction reaction. Again, you can have silicon tetrachloride reacting with hydrogen to form silicon plus HCl. You can also have an oxidation reaction, SiH4 reacting with oxygen to form SiO2 plus 2H2. You can write a similar reaction for nitridation and so on. In all of these, the material that is formed is deposited onto the wafer. So there are many variations to the CVD process. We won't go into them in detail. The most common method is doing CVD under atmospheric conditions. So atmospheric pressure. You can also do CVD under low pressure. The growth rate is lower. This process is called LPCVD. ALD is another process which is called atomic layer deposition. So here you are again growing material layer by layer. So the growth rate is very small. But you can have very precise atomic growth. So ALD is actually just a variation of the CVD process, where instead of introducing the two gas together, one gas is introduced which forms a monolayer. It is then removed from the system. The second gas is introduced that reacts with the first monolayer in order to form a material. So you are essentially growing material monolayer by monolayer. Another technique is called MBE, or molecular beam epitaxy. So in this case, molecular beams of the final film you want is used in order to grow your materials. MBE can be used for growing again thin epitaxial layers with very good composition control. For example, to grow gallium arsenide, you can have molecular beams of gallium and molecular beams of arsenic, both of which impinge onto your surface in order to form gallium arsenide. You can also introduce your dopants along with it if you want to form N-type or P-type gallium arsenide. So these are some of the examples of CVD growth processes. Usually some sort of hard mask is used along with these growth processes so that the rest of the wafer is protected and the growth takes place at the region where you want. So in next class we are going to look at some of the physical vapor deposition processes, especially those that are used to form metals. So this is called metallization, and we will also look at polishing the wafer in next class.